If you were to walk your car up, it would start up today, and you would expect the same thing tomorrow. We're used to reliability and things like that, and when it doesn't work, it's a great problem. However, think about the drug effect in an experiment, right? Developing drugs, we hope, will be helpful for addressing the pandemic. That's why we're all virtual. So if a drug has an experiment, will have the same effect if it's prescribed today. And that gets at the heart of what is considered to be the replication crisis or reproducibility crisis. Oh, and in our field, we have a virtual object that we see in the location. We hope that that object will be perceived in the same location when anyone else looks at it. So here are some titles that have appeared over the past 10 years in the popular press. So in 2010, in The Atlantic, Damned Life in Medical Science. In The Economist, article titled Unreliable Research, Trouble the Lab. Why most research findings are false. Believe it or not, how much can we rely on data on potential drug targets? Cancer research in crisis. Are the drugs we count on based on bad science? If you have cancer, you certainly want your drugs to be based on science. And finally, science is broken. All the articles that I read doing the scholarship for this was negative, I have to say. The problem is the failure to replicate published findings, even findings in textbooks. And the reason that is given for these failure to replicate are research biases. Publication bias, and this is because significant results tend to be published. Selection bias, so only significant results tend to be selected for analysis. And that leads to reporting bias. So we write papers and only results are reported in those papers. Replication studies is a study where we try to repeat the results of the studies, are rarely funded and therefore rarely published. And there's little incentive to do them. Because of that, most conducted studies are exploratory in nature. So this is the problem that authors of the papers that we just looked at are referring to when they talk about the replication crisis. There are questions about this. Okay, looking at the little characters here. So what are the evidence? You see this here, I think, well, is this actually a problem? Where's the evidence? So here's some of the evidence. In the field of cancer biology, in 2011, there was an analysis. 95% of cancer drugs failed in clinical trials. So when this came out, it was shocking to people in medical science. What do you mean 95% of the drugs failed? It's a huge waste of effort. So to replicate these on drug effectiveness, and makers of Amgen both funded these. Fields, they're different replication studies. So everything I'm talking about it became a concern in the larger field of science in the past 10 years. So check out the number here. So the Bayer study, only 2% of replicated. The Amgen study, 1%. A study by the National Institute for Neurological Disorders, only 8%, 1 out of 12 replicated. The first was for ALS Therapy Development Institute. So ALS, Lou Gehrig's disease, that's a terrible disease, really terrible disease. And none of the findings were replicated, 0 out of 47. So very distressing. And finally, the project that this tutorial is going to cover in some detail, the reproducibility project in psychology. So those replication studies were all conducted in biomedicine psychology. In addition, there were some surveys. This question: have you failed to reproduce somebody else's experiment? And here are the percentages of the responses that said yes. So 87% chemistry, 77% biology, 6% in physics engineering, 7% in medicine and earth environmental science. It's like very high numbers in terms of not being able to produce the findings. So what is the importance of replication? So here's another way to express the importance of replication. What I wanted, hang on my, oh there, all right. So in 350 BC, Aristotle sought to explain observed phenomenon to objects on Earth. He observed that light fall slower than heavy objects. Now, we don't actually know that Aristotle was by rock, but those at the time that Aristotle did this, experimental science. His was that heavier objects fall faster. In other words, their acceleration would be proportional to mass. So I can't see people their head no, but right. Okay. He did not consider air resistance. It was the accepted theory for thousands. So say he tested. In other words, he created air theory by dropping things from the tower. He dropped a musket and these are of a similar density, and he found that they fell at the same rate. So that object rate, so a constant acceleration according to. So this is an example of replicating a known experiment. Replication was done, and original explanation were uncovered. So then, in 1971, David Scott and team at the end, he dropped a hammer and a of the moon. And I guess oh, no, it stopped playing when I did that. And so the setup is David, the commander of Apollo 15, and in the last moon, last time that humans were on the surface of the moon, period. 1971, 49 years ago. Seems like it's too long ago. He dropped a hammer on the surface of the moon, where the air resists. And you can, and they fall around at the same time. He says that we got here today was because of a he was referring to the feather and rock, Aristotle, and Replication. Pretty cool, huh? Any thoughts or questions about any? Please raise it. Okay. So that's an introduction to the replication crisis. So now we're going to talk about reproducibility and inferential statistics. I'll talk a bit about hypothesis testing. This is going to give us a technical background that will then allow us to take out the reproducibility project from psychology in a deep way. So, hypothesis testing, what is the goal? The goal is to infer population characteristics from sample characteristics. So suppose we're interested in something like showing a virtual environment in stereo make it more effective, will make people faster at doing some tasks. So we go out, we collect samples, and we get, species. They have this nice normal shape here, so we fit a curve to it. The samples might be 20, 30, 50 people. It's not that we're interested in those 50 people. We want to know about the entire population, which those people were drawn. We want to talk about the effects on the whole population. So when we run an experiment, what are the possibilities? There are two possibilities. One is that the time to navigate in stereo is different from the time to navigate in mono. And that's the case for what we see here. If these times are different, then different in ways. The time to navigate could be different, but the two populations could be close together. Or the times to navigate, the mean time, the middle time, could be different, and the populations could be apart. So that's one possibility, that there are two populations. The other possibility is that there's only one population. And under this possibility, all of the data is going to be drawn from a single population. So the purpose of hypothesis testing is to figure out which one of these is more likely. Are there two populations, or is there one population? You can theoretically clear that if there are two populations and the populations are far apart, it's going to be relatively easy to determine if there are two populations. But if there are two populations that are together, it's going to be hard to tell the difference between this alternative and the alternative. So to answer this question, an empirical science developed a procedure for hypothesis testing. And this is the logic of the procedure. So we developed a testable hypothesis. We call that H1. In this case, this would be the hypothesis that subjects are faster when viewing the scene in stereo. And so operationalize that by saying the difference between stereo and mono is some number from 0. We then have the null hypothesis. This is the logical opposite of the testable hypothesis. And so this is that the difference between stereo and mono is equal to 0. Then construct a sampling distribution assuming the truth of the null hypothesis. We run an experiment, we collect samples, and it gives us a sample statistic that we call X. So for example, subjects of mono and stereo. Then, for the sampling distribution, we calculate the probability of seeing X given the null. We have a question from Alex. So can you just ask, or mute you or something? Let's see.
I can ask myself. We are having very big interruptions of your audio here. Sorry.
Okay.
I think it's better if we resolve it right now before we move forward. Because it's everywhere. Everybody has difficulties hearing you.
Okay. Let me check something that might be the cause of it.
I heard that you set the microphone already to maximum sensitivity. Can you try switching the microphone in your settings?
Hang on, I'm checking things. Okay. Now I'm going to see what the setting is again for the hello? Can I hear you?
I can hear.
Okay.
Yes, but you're still being interrupted all the time.
I'm still what?
It's like noise. We can hear your voice, and then we have like constant.
Ah.
So like the microphone is not picking up everything that you're saying.
Check, check. All right. Check, check. Too much. Check, check. Okay. I just changed some more things. Does that sound any different?
It's a bit.
Of course, I don't know why that's happening because I'm teaching here using the same setup. So why would it be different now? Is it better?
Yeah.
Okay. So our thing, as well, he's in the same room as me, and it's better for him. So Alex or anyone there, feels not very bad. Please go. And we will still continue. Okay. So we're talking about the hypothesis testing procedure. We develop a testable one, then we develop the opposite, null hypothesis. Then somebody has changed the settings. That's fine. What can I try here that's different? It hasn't been tried yet. I take it things still sound bad. Is that right? So let me try other things. Okay. There's a lot of resources. I'll get rid of that. And what else can I do here? Not really running anything else that I think would take resources.
Have you tried switching the microphone that you're using?
Switching to another microphone.
Yes, yes.
Okay, although the one I have is a professional meeting microphone, so I'm going to change it there, but I will try like the built-in one. Nothing to do with the connection, though, in which case Yeah, I know. I need to change. I need things this.
I can hear you.
All right. Input. Go here. Active microphone is. Did I?
Yeah, I can.
Oh, now can. So it's possible to now be heard. Now. So
We can hear you, Ed.
okay, good. Okay. So I will attempt to continue. All right. Is it better? Okay. So we have a hypothesis testing procedure. And we first develop a testable hypothesis and logical opposite, null hypothesis. Sampling distribution, assuming the truth of the null hypothesis. And then we run an experiment, collect samples, builds a sampling statistic, X. So in other words, we measure subjects under conditions of stereo and mono. And then, referring to the sampling distribution, we would calculate the conditional probability seeing X, the null hypothesis. So that probability is shown here. So the probability seeing the null hypothesis is true of seeing X. If probability is low, then we are unlikely to see X when null is true. In that case, we reject the null and we embrace the alternative hypothesis. If the probability is not low, so P is greater than 0.05, we are likely to see X when the null is true. In that case, we do not reject the null hypothesis. So let's apply that to the example of stereo viewing. So the hypothesis is that subjects are faster than the condition of stereo viewing. The null hypothesis is that subjects at the speed, whether stereo or mono. So we construct the sampling distribution, assuming the truth of the null hypothesis. And then we ran an experiment, we collected samples. Experiment published back in 2003, 32 participants. We collect 128 samples. And what we found is under stereo, it took about 36 seconds. 34 seconds. Notice stereo was in the wrong direction. It took longer under stereo, which is not what was hypothesized. The difference between these two, 1.8 seconds, close to 2. And calculated the conditional probability of seeing 1.8 seconds, assuming the truth of the null hypothesis, and the probability was 0.45. And so we're likely to see this when the null is true, and therefore we do not reject it. This experiment did not tell us that subjects were faster. Their stereo would be. So there's another message. See the message, or maybe well, sure. I think someone sent me a message, but I don't know how to find the message. So,
Cross the Alex, Jack, and
what's it?
yep.
Okay. Not sure what that means. Anyway, I hope I can still be heard. You can hear me?
Yeah, I can hear you.
Yeah, of course you can hear me normally. All right. It's one example. It's the same example from another experiment that was looking at the effect of intensity on the included layers in augmented reality. So here we tested conditions of constant versus decreasing intensity. Our hypothesis was that subjects would be faster under the case of decreasing intensity. The null hypothesis here is that the subject's same speed, whether constant or decreasing intensity. We conducted a temporal distribution assuming the truth of the null hypothesis. Ran an experiment, we collected samples. In this case, 8 participants and many more samples because this experiment is more of a psychophysical character where each task took a couple of seconds. So, under the condition of constant intensity, we got 2,500 seconds. Under decreasing intensity, 2,330 seconds. So the difference between these two is about 1/4 of a second. But the conditional probability of t in 1/4 of a second, assuming the truth that is only one distribution, and that's low. That probability is 0.008. Since this is low, less than 0.05, less than 0.01, we're unlikely to see more of a second difference when the null is true. So the null when we break the hypothesis, and this experiment suggests that subjects are faster under the condition of increasing intensity. Are there any thoughts or questions about this? Hopefully, all of you are hearing me. Okay. So let's undertake some considerations. So the conditional probability, much of statistics involves here it is. Much of statistics involves how to calculate probability. This is the source of a lot of the complexity of a statistical analysis. But the logic of hypothesis testing is the same, regardless of how the conditional probability is calculated. And if you can calculate the conditional probability, then you can test a hypothesis. The null hypothesis, it's usually a form of some function of means of population statistics being equal to 0. This is the double negative logic. We assume the null, that's the opposite line, and it will happen, and then we choose to reject the null hypothesis. There's a philosophy here that you can never prove that f is equal to 0, because 0 is a point value in the domain of real numbers. This is the same with a computation that you do with floating point numbers. If you do a computation, which is a graphics computation or simulation, you calculate some number. If you compare it, is that number exactly 0? Or is that number exactly any integer? Then the answer will be no. Because what are the chances that a floating point number would be exactly equal to 0? But of course, you see whether the floating point number is within some range of the number. So the hypothesis is always in this form that the function does not equal 0. We don't know what value it will take. Main interest at 0. Okay, what does it mean to reject the null hypothesis? What does that mean? In science, generally, we reject alpha equals 0.05. But I want to point out that this is a social convention that was adopted by early statisticians. There's nothing magic about the number 0.05. What can we say when we reject at 0.008? Thing we could write in our paper that is completely faithful to the logic of hypothesis testing. We can say if the null is true, then there is only a 0.00 probability it results, and this is unlikely. So that's correct. Here's something that is often stated or implied in papers, but in fact, there is only a 0.00 probability that our result is an error. This is wrong. It refers to probability, but that's not what we calculated. Sometimes something like this is written. There is only a 0.008 probability that the null could have been true in this experiment. That's wrong. That refers to the probability of the null given the sampling statistic, but that's also not what we calculated. Are there any thoughts or questions about this? Okay. So what does it mean when we don't reject the null? What do we say when we don't reject the null? So the example we saw was 0.445. We've proved the null is true. Can we say our argument indicates that the null is true? You're both wrong. Hypothesis testing cannot prove the truth of the null hypothesis. In fact, statistics generally disagree on what failing to reject the null means. The conservative viewpoint, which was adopted by Fisher, first person to really articulate the logic of hypothesis testing 90 plus years ago, is that you suspend judgment. You can't say anything about the truth of the null hypothesis. An alternative viewpoint, by Neyman and Pearson, is that we accept null with efficient experimental power and a low probability of type 2 error. So here's a big my hypothesis testing is because hypothesis testing uses probabilistic, but humans intuitively think of reasoning as absolute. Now, hypothesis testing follows the logical rule of modus tollens. That means the mode that denies. And you can derive the mode that denies through a simple truth table, as you might see in a class on logic or maybe discrete mathematics. So, if hypothesis is absolute, then this is the chain of reasoning. The null hypothesis is true, then X cannot occur. However, X has occurred. Therefore, the null hypothesis is false. So that's what's shown here. If the null hypothesis is true, then X cannot occur. However, X occurs. Therefore, the null hypothesis is false. So here's an example. If first is a Martian, then they are not a member of Congress. This is true, right? Talking about American Congress. Sometimes in America, we see these people, but let's assume that they're not. This person is a member of Congress. Therefore, they're not a Martian. So here we have a correct result. But consider this. The person is American, then they are not a member of Congress. False. This person is a member of Congress. Therefore, they are not an American. So this is an incorrect result, but the correct logical reasoning, where we've just replaced Martian with American. So this is if hypothesis testing was absolute, but it's not. Hypothesis testing instead is probabilistic. So that looks like this. If the null is true, then it's highly unlikely. That's not the same thing as false, though. However, X has occurred, and therefore the null is highly unlikely. So if a person is American, then they are probably not a member of Congress. This is true, right? So there are 150 members of Congress in America. There are about 300 million Americans. If you number by the other, you get 0.00002. Experiment, we would love to see a p-value that low. So if a person is American, they're probably not a member of Congress. This person is a member of Congress. Therefore, they are probably not an American. This is an incorrect result, but it is a correct example of hypothesis testing. Are there any questions or thoughts about this? I hope all of you are hearing me. Okay. And yes. Alex has a question. Alex.
Can
I do what? So you asked me something, but I'm not sure what you asked me. Here, I'll start at my if he sent me a mail.
Green break.
Say I was about to break itself. I don't see any email from him directly. So for some reason, I don't see his text anymore. So I can't see text anymore. But man,
Alexander?
so
Maybe I can explain to Ed, because Alexander has some connection issues. Ed,
now I can hear Francisco talking.
yeah, exactly. Okay, Ed, I was discussing with Alexander because your voice is having some cuts. So I don't know if you have some earplugs with Bluetooth or something, because other presenters had this issue this morning. If not, I was asking you to have some small break so we can test this out to try to see if we can improve that.
Yes,
I don't know
I'll take
if
a
you have
break
some
anyway
planned break.
because I've been. I will take a break. So let me make a public announcement. Type.
Okay, just some 5 minutes we can test it out. I'm really sorry, Ed, because it's
All
a
right.
bit difficult to hear you.
I am impressed with it. I mean, I can't see anybody's face, but
Yeah.
all right.
Okay, do you prefer us to go outside again? It's going to be better, I think, so we don't disturb the others. Okay.
Want me to unplug this?
Because if you, yeah,
What?
if you, okay, you have other microphone there. You have, I think it's big to test.
Verbella.
So I do something in Verbella.
I do something
okay?
in Verbella.
No, it's okay.
No,
It's okay. Yeah, just stop sharing your screen in Verbella.
Just stop sharing your
Okay, I
screen
think I
in
have to-
Verbella.
1, go.
Go. All right. I don't know how much of the first part of the tutorial anyone has heard, but I'm gonna keep going. So so we were talking about reproducibility and inferential statistics, and we talked about hypothesis testing. We tried to talk about hypothesis testing anyway. And let's see, I can't see anyone here, so I'm going to move these. Put these here, I guess. Okay. So now we're going to talk about reproducibility, inferential statistics of power, effect size, and p-values. So when we run an experiment, the experiment generates this 4-cell decision table. So the first thing to consider when running an experiment is what is the true state of the world? Either the null hypothesis is false or the null hypothesis is true. So there are 2 possibilities here. Then we make a decision. Either we reject the null or we don't reject the null. And so there are 4 possible combinations here. Furthermore, if the true state of the world is that the null hypothesis is false, then we can visualize that as drawing a distribution from, as drawing a sample from this distribution here, this pink one. If the null hypothesis is true, then we can visualize that as drawing a sample from this blue distribution here. So if the null hypothesis is false, so we're drawing our sample from the pink distribution, then we want to be correct. And so we set the alpha value, 0.05 usually, as the area under this distribution over here. And so 95% of the time, we will be selecting by random chance, our sample will come from this part of the distribution. 5% of the time, it'll come from here. On the other hand, if the true state of the world is that the null hypothesis is false, in other words, the alternative is true, then our sample comes from blue here. And in that case, it is this boundary here from which our hypothesis decision will be made. So when the null hypothesis is false, and our sample comes from here, if we get the sample from this part right here, then we will not reject the null hypothesis. This is what we call a type 2 error. A type 2 error means that a result was there, but we missed it. As you can see from here, the probability of a type 2 error is beta. On the other hand, if the sample comes from this part here, then we have a result. The null hypothesis is false, and we reject the null hypothesis. And the probability of that is 1 minus beta, which is what we call power. However, suppose that the null hypothesis is true here. In that case, our sample is drawn from this pink distribution here. In this case, if our sample happens to come from this part here, the part under alpha, we have a type 1 error. A type 1 error is we think we have a result, but we are wrong. We don't. On the other hand, if by chance the sample is drawn from this part, then the null hypothesis is true, and we do not reject it. So that's correct. But then, of course, we are stuck with the fact that we're trying to argue the null hypothesis. So this is the relationship between alpha, 0.05 number, beta, and power. So we want to run powerful experiments. And the next 4 slides are going to show different ways of increasing power. So we can increase power by increasing alpha. So here we have the same diagram we just looked at. And here we have the same diagram, but we have increased the alpha value. So when we increase the alpha value, going from top to bottom here, we increase the power, we decrease the probability of a type 2 error, and we increase the probability of a type 1 error. When we decrease alpha, going from the bottom to the top, the opposite things happen. We decrease power, we increase type 2 error, and we decrease type 1 error. So all of this illustrates the trade-off between alpha and power. Here's another way to to increase power. We can increase power by measuring a bigger effect. So here we have the same diagram we've been looking at. The effect size is the distance between these 2 distributions. Here we have the same 2 distributions, but they're farther apart. So when the effect size gets larger, going from top to bottom here, as you can see, power increases, type 2 error decreases, and alpha type 1 error, probability of that stays the same. This is another way of pointing out, unsurprisingly, that large effects are easier to detect than small effects. We can also collect power, increase power, by collecting more data. So here we have our power diagram. If we collect more data, the variance of these distributions decrease. Because these distributions retain a constant area under the curve of 1, when the variance goes down, the distributions become more narrow and taller. Here, as you can see, the effect size remains the same. So when we collect more data, the variance decreases, the power increases, type 2 error decreases, the probability of that, alpha and type 1 error stays the same. So collect more data, you have more power. We can also increase power by decreasing noise. You'll notice that these 2 slides graphically are identical. And that's because decreasing noise has the same effect as collecting more data. So if you can run a higher quality experiment, an experiment with less noise, then you can increase power. Are there any questions about power from the slides we've just looked at? I suppose now when I ask that, I'm looking at the Zoom call. I see 5 people on that. And I guess I see the same people in Verbella as well. All right. So how do we use power? So power is a relationship between 4 different numbers. It's a relationship between power, alpha, the effect size, and the sample size. A problem for our field is that the effect size is generally hard to know. Population parameters, like effect sizes, are typically estimated from prior studies. Our field is new, so there's not many prior studies. But if you do try to replicate a previous experiment, then you also start with an estimate for effect sizes from that experiment. Some people, some authors, engage in post hoc power analysis. So for post hoc power analysis, you estimate the effect size according to the difference in the sample means that you measure. But you can't do this for the same experiment that you've just run. I mean, you can, but it's pointless to do it because the effect size within the same experiment contains exactly the same information as the p-value. So the p-value also serves as a measure of effect size. The smaller the p-value, the larger your effect size. The larger the p-value, the smaller your effect size. So in an experiment, it's pointless to report a power analysis from an effect size that you've measured in the same experiment. Are there any questions about that? So here are some other uses for power. So the most common way to use power is to determine the number of samples that are needed to achieve a certain level of power. So we calculate n as a function of power, alpha, and estimated effect size. This gives a rational basis for deciding n. Cohen, who is considered the father of power analysis, recommends an alpha level of 0.05 and a power level of 0.80, which would be equivalent to a beta of 0.20. So he recommends basically a ratio of the probability of a type 1 error to that of a type 2 error of 1 to 4. You can use power to determine an effect size that will be detectable. So how big of an effect can you detect at a certain level of power, alpha value, and effect size? And finally, you could use this to determine a significance level. So power is a four-dimensional relationship, a relationship between four numbers. And you can calculate any one of those numbers from the other three. So the most common usage for power analysis is number one. How many samples are needed for a certain power? Final topic in this part, arguing the null hypothesis. You cannot directly argue the null hypothesis. Again, as we discussed, although I don't know if I could really be heard at that time, we can't directly argue the null hypothesis because it's like trying to argue that a floating point number is exactly equal to a certain integer value. But we can argue that an effect size is bounded by a small enough number, d. If d is small relative to the experimental conditions, then you've effectively argued the null hypothesis. So in other words, if you have a virtual environment that takes on average 1.5 minutes to navigate through, you might decide that if the difference between stereo and mono is less than 5 seconds, that's not enough of an effect size to make any practical difference. In that case, if you could show that your effect size was less than 5 seconds, you would effectively be arguing the null hypothesis. Are there any questions about that? Okay, I don't see any questions. Looking around. So that's a brief background on reproducibility and inferential statistics. With that as a background, now we can talk about the reproducibility project in psychology. Am I still coming through clearly as far as you know?
I actually didn't check the Zoom because if I join the Zoom, then it'll be good. So.
Oh, okay, okay. I assumed someone would say something.
I think Alex was there, so.
Okay.
We'll let you know.
All right. So let's talk about the reproducibility project in psychology. We saw previously that there were these, there have been a series of systematic replication studies. And we're going to study the last one, reproducibility project in psychology, in some detail. This project was begun by Brian Nosek. He's a professor of psychology at the University of Virginia in 2011. And this project resulted in a paper. And I'm going to show you a picture of the paper. And so here's a picture of the paper. This paper is called Estimating the Reproducibility of Psychological Science. And notice that the author is the Open Science Collaboration. So if we go down to the bottom of the paper, maybe I'll make the paper fit here. There we go. If we go down to the bottom of the paper, the Open Science Collaboration is a whole lot of authors, and only one of which is Brian Nosek. So this is the paper that this next part of the graph is studying. This paper was in the journal Science. So this paper replicated 100 published studies in the field of psychology, recruited a very large team, so the Open Science Collaboration has 270 co-authors. So the first part of this was to figure out which studies should be replicated. The goals here were to minimize selection bias, maximize generalizability. Therefore, as part of the project, before it was done, the group published a sampling frame and selection criteria. And so here's what these were. So this project covered 3 leading journals in the field of psychology. It covered Psychological Science, which is considered the premier outlet for all of psychological science. And then the Journal of Personality and Social Psychology, which is considered the leading journal for social psychology. And then the Journal of Experimental Psychology, Learning, Memory, and Cognition, which is considered the leading journal for cognitive psychology. So the sampling frame included the first 20 articles in each journal, beginning with the first 2008 issue, and then 10 more articles as needed to come up with enough experiments to try to replicate. within each article, the goal was to replicate the last study in the article, unless for some reason the last experiment was infeasible. So generally, the last study in each article is the most definitive. Early studies typically are more exploratory in nature. So 84% of the replicated experiments were the last study. The result had to be in the form of a single inference test, usually a t-test, an f-test, or an R correlation. And if available, the replication used the original materials. And the replicators would seek design feedback from the original authors. So by definition, each of these had a power because the effect size from the first time the experiment was published was available. So enough participants were recruited for high statistical power. That is a power greater than 0.80. And so here are the results of the articles selected. There were 488 articles in the 2008 issue of the 3 journals. 158 were available for replication, 113 were selected, and 100, exactly 100, were completed by the deadline. Just by chance, it was exactly 100. So some of the issues addressed were, how do we measure a replication? How do we quantify a series of replications? Each experiment was analyzed with a standard R package that the team created, and each analysis was replicated independently by a second team. So here are the study characteristics. The original study had a p-value, the original experiment, had an effect size, it had a sample size, or for experiments where each participant provides multiple pieces of data, degrees of freedom. And then the importance of the result was rated by the other authors. The surprisingness of the result was rated by other authors in the open science collaboration. And then the experience and expertise of the original team was rated. And, oops, drop my mic for a moment. And then here is the results of the replication study. So we had a p-value, effect size, degrees of freedom, power can be calculated here. How challenging the replication was, the experience of the replicating team, and finally the quality of the replication. Any questions about any of this? Okay, so now we're going to look at the results in several different graphs. So first, we're going to look at the p-values. So these are violin plots. In a violin plot, the width is proportional to the density of values at that level. These are also broken down into quantiles. As you can see, the 25th quantile is barely visible because it is so close to 0. So looking at the original studies, 97 of the original studies had a p-value of less than 0.05, which is this dotted line here. And 4 had a p-value of 0.06, but that was treated as significant in the paper. Look at the p-value of the replications. So here the median p-value is, say, a 0.23, and the 25th quantile is quite low, but the next quantile, most of that energy is above 0.05, and then half of the p-values are up in here. So clearly, the p-values went up a great deal in the replications. This graph looks at the effect sizes. So here are the effect sizes of the original studies. And the effect sizes here are all turned into correlation coefficients, so between -1 and 1. By definition, original studies all had a positive effect size. But if the effect flipped in the replication, then the effect size went negative. So I started this talking about whether or not people who viewed a virtual environment in stereo would have a faster time going through the environment or not. And so that's an example where if the original experiment had found that people in stereo were faster, and then if in the replication the people in the experiment in stereo were slower, then that would be an example where the effect size would flip from a positive number to a negative number. So the visually obvious result here was that the replications had a smaller effect size than the original studies. So this interesting graph is a way of looking at all of these effects on one graph. So here's the original effect size along the x-axis, 0 to 1, normalized effect size. And up here we have a density plot. This is the distribution of effect sizes. And blue here, greenish blue, are for the significant effects, and then red right here are for the not significant effects. Then the replication effect size is on the y-axis, and this goes from -0.5 up to 1. And so here we see for the replications that were significant, this is the distribution of effect sizes. For the replications that were not significant, here is the distribution of effect sizes. And you can see that effect sizes, that distribution, there's a peak around 0, in fact. And this line here is the 45-degree line. So if the original study and the replication had the same effect size, then that study will show up as a dot that lies along this line. So dots close to the line were studies where the original and the replication had the same effect size. Dots above the line are for replication studies where the effect size went up. And dots below the line are replications where the effect size decreased. And finally, the greenish blue dots were significant replications, and the reddish dots were non-significant replications. So the story here, oh, and then the power of the replication is also indicated by the size of the dot. So the story here is that the replications had adequate power, but the effect sizes fell considerably and significantly when replicated. So here are some more qualitatively stated results. So one result is that the initial strength of evidence predicted the success of the replication. So for experiments with a low initial p-value, 63% of those replicated. Experiments with a p of less than 0.02, 41% replicated. A p between 2 and 4, 26% replicated. P-value less than 0.04, 18% of those replicated. So, unsurprisingly, the stronger the original finding, indicated by a low p-value, the more likely the study was to be replicated. Wow. Also, cognitive psychology was more successfully replicated than social psychology. So about 50% of the cognitive psychology experiments were replicated, but only 25% of social psychology experiments. So cognitive psychology experiments tend to employ repeated measures designs. And in our field, we also tend to employ repeated measures designs. And these designs are usually more interested in how participants react to different interface designs, less interested in how people themselves differ. So repeated measures designs are also common in our field. And so there were weaker original effects in social psychology, more within subject repeated measures designs in cognitive psychology. Main effects were more successful than interactions. And main effects typically have higher power. They were more repeatable. Now here's also some very interesting results. So surprising effects were less reproducible. If people were surprised by an effect, it was less likely to be reproduced. Journals and conferences like to publish results that are surprising, but they are less likely to be real effects. Experiments rated as challenging were less reproducible. That's also not surprising. If the experiment is complicated, challenging somehow, then it's harder to make a good measurement with it. The original result, the importance of the original result, that had little effect on how repeatable the experiment was. And the team experience and expertise had almost no effect. And finally, the quality of the replication had almost no effect. So all of these are negative correlations. We have already seen the main positive correlations in the previous graphs. Larger original effect sizes were more reproducible. Larger replication effect sizes were more reproducible. And more powerful replications were also more reproducible. So to summarize the findings of the replication project psychology, even though the replications used materials from the original authors, were reviewed in advance for methodological fidelity, had high statistical power to measure the original effect size, the replications produced weaker evidence for the original findings. The strength of the initial evidence, the p-value, the effect size, that predicted replication success. The characteristic of the teams and of the original finding had no impact on replication success. So this raises the question, why were there so few replications? The hypothesized reasons were what we talked about at the beginning of this tutorial. The biases we mentioned, the publication bias, the selection bias, the reporting bias. So, because of the publication bias, only significant results were published. Because of the selection bias, only significant results were selected for analysis. And because of the reporting bias, only significant results were reported in the paper. Therefore, the effect sizes of the original studies were inflated. Now consider the replications. All of the results were reported, so there was no publication bias. And all of the confirmatory tests were based on publicly disclosed pre-analysis plans. That means there was no selection bias, no reporting bias. So a lack of bias is likely a big part of the reason why there was so few replications. Are there any questions about any of this? I definitely encourage questions or thoughts. In that case,
Actually, I do have a question for you, Ed.
All right.
As the replications were, I mean, the numbers of the replications, they're actually quite small, right? So even if it's 80% that were replicated, could it be that this is biased again by small sample size?
Well, they chose sample sizes that were large enough to meet the 0.80 power threshold.
No, I don't mean the studies themselves. I mean our conclusion from the number of studies.
So the so 36% were replicated. That's the final number. Is that what you were asking?
Yes, but well, my question was the 36% is based on, I think, 100 studies or something like this?
Yeah, it's exactly 100. By chance, it was exactly 100 studies. So 36 of them were replicated.
Yes. So what do you think, how likely is it that this 36% is by chance? That if we expanded it to 1,000 or 2,000 studies, we would have maybe 70% or 60% or 5% replication?
Yeah, that's a good question. So the answer would be, how reliable is that measure of 36%? And it's really unknown. This is by far the largest replication effort in psychology, I believe. And the only way to know how that would, what the number would be in other fields, like say our field, would be to try it and find out. There's no way to be able to tell, what it'll be ahead of time. So, but in the second part of this tutorial, Arifin is going to discuss some other replication studies from other fields. That's a good question. Are there any other questions? Okay, so we're going to consider then what this means, but I am now going to take another 5-minute break and give my voice a break from talking. But apparently my voice sounds better now, and so I'm glad of that. So let us take a break, and maybe that could be an announcement as well. Okay, so take that break. And then I'll probably be in the meetings.
Yeah.
I've got nearly 2 hours. And I was going faster because it's All right, I am back. I hope other folks are back. Hope I can be heard still.
Yes.
Okay, great, great. So we talked about the replication crisis, inferential statistics, and we covered in some detail the reproducibility project in psychology. So now we're going to talk about what does that mean? Oh, hang on, there we go. So why might an experiment be irreproducible? Suppose a study finds A is a result, but the replication does not find A. Why? Perhaps the original study is wrong. In that case, the truth is that A is not true. And that's why the original study found A, the replication did not. It could also be that the replication is wrong. In that case, A is actually true. But there is a third possibility here. The third possibility is that both the original study and the replication are correct. And in this case, A could either be true or false. So how could number 3 be the case? It could be the case because many things can differ between two studies. The experiments, the participants, the methods, the equipment, the analysis, and there can also be random variations. The type 1 error, the type 2 error, so forth. So the story of Aristotle, Galileo, and astronaut David Scott, that's a case in which number 3 is the case. For Aristotle, the original study was correct considering air resistance. So the rock did fall faster than the feather. Aristotle didn't know about air resistance. So the replication was also correct, considering air resistance. The two metal balls fell at the same rate, even though one was definitely heavier than the other. So both of these were correct studies. In this case, A was Aristotle's original theory, the theory that objects fall at a rate in a gravitational field that is proportional to their mass. That's what was false. So some reproducibility scholars, like Brian Nosek, they believe that number 3 is the most common reason for studies to not be reproducible. Any thoughts about this? It's kind of a philosophical idea. Other reasons: first impressions are often false. Aristotle's first impression was wrong. It can be hard to detect the difference between a real result and noise. So this is likely the reason for the low reproducibility in the social sciences. And finally, if enough hypothesis tests are conducted, you can usually find something. So if you do enough, eventually you'll get a positive p-value. Now, this could be controlled by adjusting something called the family-wise alpha level. But the main reasons for irreproducibility are that the incentive structure of science does not maximize the yield of true results. So we are incentivized to find significant, novel, surprising results. The result, if we find those, are papers, funding, degrees, career advancement. These incentives result in many exploratory studies in every field. But if a finding is spurious, we're not going to find evidence for that until a replication is attempted. So if a study finds A, and the replication study also finds A, what does that mean? It means that A is a reliable finding. But what about the theoretical explanation for A? That explanation might still be wrong. That was the case here. So Aristotle's original explanation was wrong. So understanding the reasons for A requires multiple investigations. There might be errors, there might be probabilities, and the theory itself, the explanation, might also be wrong. So multiple investigations provide converging support for the true theory and eventually rule out alternative or false theories. So empirical science really requires multiple investigations, that is, replication studies. Any thoughts or questions about that? I'll look at this because
Hello, I have a question about
okay.
what do you mean about multiple investigations? I mean, discover all the reasons why your results that like
So multiple investigations would be Aristotle conducted this experiment, had the wrong explanation for it, for the findings. That helped, that explanation was accepted as the truth for about 2,000 years until Galileo tried to systematically reproduce it. So generally, multiple investigations would be that important findings are tried again, maybe by the same lab, maybe by a different lab. But it's basically taking important findings and repeating the experiment to see if the same thing occurs or if something different occurs.
okay, so it's not just assume that's true, right? It's
That's
multiple
right.
testing, multiple testing.
Because in empirical science, when you run an experiment, it may be true, it may not be true,
But how do you know that you tested enough?
well, you don't. So
Okay.
there is converging support for the true theory, but eventually people believe that the evidence for a certain theory is overwhelming. So we could list global warming as such a theory. You know, there's been an overwhelming number of studies. But, you know, it's a human construct when we choose to believe it. And sometimes humans choose to believe something that is actually wrong. So Aristotle had the theory that objects accelerate in gravitational fields in proportion to their mass. That was wrong, but people believed it for 2,000 years. So we don't know. And multiple investigations help increase confidence. But any kind of empirical science has this inherent probabilistic nature to it.
But I mean, you don't have any kinds of right amount of tests to perform, right? You don't have such things.
No. Now you can use power analysis to come up with a number of participants that is, based on trying to achieve a power of a certain numerical value, like 0.80. But aside from that, there's not a magical number of replications that where your confidence can go up to 100%.
Okay, thank you.
Okay. How is it that keeps happening? Okay. So another thought, how many studies should be reproducible? The Reproducibility Project found that 36% of the experiments were reproducible. Is that too small? Think about that. Is that too small? What if 100% were reproduced? What would that mean? So 100% reproducibility would mean that we are never surprised. It would suggest that we always know what will happen and why it will happen. And that would raise the question, why are we running these experiments in the first place? 36% feels like it's too small. 100% would definitely be too large. So the perfect percent of reproducibility, that likely depends on the field and the subfield. This is related to what Natalia was just asking. This is related. It's likely unknowable. We don't know what it should be. It seems like it should be higher than 36%. Progress requires both kinds of experiments. It requires exploratory studies where innovative and new ideas are explored. But it also requires confirmatory studies where important results are replicated. So innovation points out those ideas that are possible. Replication points out ideas that are likely. And progress requires both. So the scientific incentives that we all live under, funding, publication, awards, advancement, these should be tuned to encourage an optimal balance between exploratory and confirmatory studies in a collective effort of discovery. The problem we face as a field is that innovative new ideas quickly become old news to reviewers and editors. And so we need to try to come to some sort of optimal balance. Are there any questions about this? This is another important philosophical finding from the Reproducibility Project. Okay, so the last part of the tutorial that I am teaching, what should we do? We being the field of augmented reality, virtual reality. So the most obvious recommendation from the title of this tutorial onwards is for our field to value replication studies, and we operationalize value by accepting those papers. So we value confirmation studies. We also value exploratory studies. So it's not that we should only accept confirmation studies. We should accept both. We should value those studies that are well done, regardless of the type or the results. And this requires changing our incentive system. As people collectively running this conference, we cannot directly control things like how our funding agencies work, how the advancement systems in our places of employment work. We can't directly control those. But we can change things like how our review system for papers that have appeared at this very conference. We can change things like how that review system works. So my empirical experience in this community involves more than 25 years of writing and publishing empirical research. In addition, in the past 6 years, I have served as a general chair, a program co-chair at both IEEE VR and IEEE ISMAR. And what I have seen in the review process and acceptance process is entirely too much emphasis on novelty and surprise in the review process. So here are 3 comments from negative reviewers that I have received on papers over the past, say, 12 years. Not all of these papers were rejected. Not all of them were accepted. But, and I'm certainly not saying that all of my papers should be accepted, and I can assure everyone attending this tutorial that all of my papers are not accepted. But see, look at the, but all of these comments come from 3 different reviews that were negative, that were arguing against acceptance. So, but rather a reduction in the available cues, which makes the reduced performance not terribly surprising. This experiment tells us something important about depth perception in AR, most of which isn't especially surprising. It is not clear that this will help very much. It is not entirely surprising that participants become more accurate in feedback condition. So notice the negative reviews in each case are talking about how the findings are not surprising. The Reproducibility Project found that there was a strong negative correlation between the surprisingness of a finding and whether or not it was reproducible. So we need to educate the field, which is reviewers, editors, authors, everyone attending this tutorial, watching in some way, has one of those roles. We need to educate the field about the issues of replication and to value replication studies. Are there any thoughts about this?
I have just a question.
Okay.
You say that we had to value the replication works, but your example is that Aristotle did something wrong in the past, and through the replications, we find out that. But this replication did not confirm his studies. So we have to value just the replications that does not agree with the previous work.
Well, so Aristotle dropped a rock and a feather, found that the rock fell faster, but you know, that is something that is common human experience. I mean, all of us know intuitively that if we drop something like a feather, it's going to fall more slowly than something like a rock. So, you know, to a degree, that experiment had been replicated many, many, many times. it's an interesting story, an example of the importance of replication, but you know, it's not the kind of question that we typically ask in our experiments in this field. I don't know if that answers the question or not, but that's a thought.
Kind of. So we are just ensuring that the results are right or not?
Well, replication studies are very hard to get accepted. So I guess the point here is that based on this evidence, I am advocating that as a field, we value replication studies by changing our review system to know that a study that replicates a finding is also making a contribution to the field, because that would begin to change the incentive structure that is driving the preponderance of exploratory studies and the lack of confirmatory studies. Because again, progress requires both. But as a field, we're generally only getting one. We're not getting both.
All right, thank you.
So, yeah, thank you. So, recommendations. If we accept replication studies, people will do them. Another recommendation is to pre-register research plans. So before collecting data, create a detailed written plan. So the hypothesis, the analysis, the methods. This removes the possibility of p-hacking. P-hacking is another term for having a bias towards selecting significant results. Even better is to publicly pre-register the plan. And so the Open Science Collaboration, the group that wrote the paper we discussed, has created a Center for Open Science. And at one time they had a pre-registration challenge where they had some financial support for groups that pre-registered their study. So if you go to the Center for Open Science, it is a well-funded institute, funding from the Gates Foundation and other such places, and you can pre-register your study. So what is pre-registration? If you pre-register a study, you can put this stamp on your results, on your paper, and so forth. Another idea is to run larger studies. So more participants means more experimental power. But of course, larger studies are more expensive. Additional recommendations are to describe the methods behind the experiment in more detail. If the methods are explained in good detail, then replication is easier. Here's another problem in our field, a problem that some of us in the field are working on, even now. We have limited page budgets in our papers. So there are several solutions. One is to put additional details and supplementary material, which can be part of any TVCG publication. Additional details are also frequently included in associated theses or dissertations that the papers might refer to. We could also adopt longer page limits. And I'll point out that there is a typographical tradition in some journals, like the journal Nature, where the main paper is in a bigger font and the methods are in a smaller font. So let me show you an example of this. Okay, so here is a paper in the journal Nature, and the paper exists, it's discussed, there are results, there are diagrams, and then at the end of the paper, here are the methods. See, these are in a smaller font at the end of the paper, but they provide more details for those who wish to replicate the study. This writing style allows the paper to be read where the reader is staying at the level of abstraction of the experiment, why it was run, the results, and what they mean. But there is additional detail for the methods of the experiment given at the end of the paper. So that's a way that we could describe our methods in more detail. A method that has already been adopted by other research communities. We can also upload our materials to open repositories, and that allows easier replication. So data, materials, code can be uploaded to places like the Center for Open Science. There is also IEEE Dataport for IEEE publications. So this is IEEE Dataport, and things that are uploaded here, the promise is that they will be archivally stored, just like the digital library. And then IEEE also has something called Code Ocean. Here, you can upload an algorithm, something like that, and the system uses virtual machine technology to allow you to run the algorithm in the operating system environment in which it was first written. So the idea is that code that was written maybe decades ago on obsolete machines could still be executed. Personally, I'd like to be able to run my dissertation code again, but there's no way that code would run because it utilized SGI machines of 25 plus years ago. You know, I can look at the code, but I can't run it. There's also archive and other preprint servers, other repositories. I think these sorts of things are better than putting stuff on a personal website or something. None of us is going to live forever, but just as we sometimes cite papers of people who have passed on, but their results are still there, are part of the scientific record. You know, personal websites don't last forever either. So the final slide of this part of the talk.
Sorry, before your conclusion, I can make a question.
Sure.
I have seen about the new president of IEEE, and in the statement, he is the creator of IEEE Dataport, and in his statements, he tells about make more opportunities to data and analytics for open science, and incentivates the reproductive research.
Yeah, that's a reason for optimism.
Yes,
So actually, what you just said is essentially this bullet right here. This is the current zeitgeist among journals, funders, scientists. IEEE is a professional society. They're paying more attention to all of these issues.
Okay, and my question is, how you think that the president elected of IEEE thinking about this way about reproductive can impact our field?
Well, the president of IEEE, supporting the idea of reproducible science, you know, that's where things like the Code Ocean and the, what's it called? The thing I was just showing you, the Dataport, that's where these, you know, things came from. the open science collaboration. You know, that's, I mean, I think it's a very positive thing, because as this tutorial proposes, and as others have proposed, the way for all science to continue to make progress is for the right ratio of confirmatory and exploratory projects to be conducted.
Oh, okay, thank you.
Thank you. So in psychology, journals have begun publishing pre-registered studies. Scientists from many labs have collaboratively replicated earlier studies. There's the Center for Open Science that we just looked at. And this last bullet is over now, but when it was first developed, there was a $1 million pre-registration challenge where you could get $1,000 for pre-registering your study. Now you can get that stamp. So that's the end of this part of the tutorial. And next, Arifan Mohammed is going to present his part. And give me a minute to change slides, and then we will start this next part. And I'll certainly take any additional questions.
Excuse me, I just have a question about the first part of your presentation. You spoke about 3 kinds of bias. It were publication, selection, and reporting. And I think there is other biases that exist, and I was wondering if you can just tell us more about them, or give us some authors' names about other that discuss this kind of bias.
So I think you're talking about maybe this slide.
Yes.
Where we talk about publication, selection, reporting biases. So of course there's other biases too, but the finding of the reproducibility project is that these are probably the main biases behind why there were so few replications. Not sure if that's answering your question or not.
Oh, okay.
Maybe it had to do with this slide.
Yeah, I think they are the main. But for example, I'm working in virtual reality, so I saw a lot of study where I think there is a kind of peer hacking, and for me, kind of one of the most important bias.
Yeah, peer hacking is let's see. Trying to find where it was mentioned. Here it is. Yeah, peer hacking is also addressed by pre-registering the research plans.
Yeah.
So the replications in the replication study, the negative outcomes were also reported. So that, you know, addressed, or at least began to address, the issues of peer hacking.
Yeah, true. Thank you.
Now, all of these are hard problems, and like problems of culture, of research culture. And so none of them are quickly or easily solved. So let me change, going to change slide decks here. There it is. So it's this one.
Oh, yes.
Okay. Great. And I'll just take over your computer.
Oh, thank you, Richard.
Sure.
Thanks, Rohit, for your excellent talk. And hello, everyone. I'm Arifin. I'm a PhD student at Computer Science and Engineering Department of Mississippi State University. And Dr. Ed, he's my advisor. And it's really nice to talk about this replication crisis in empirical science. and implication for human subject research in mixed reality. So far, Dr. Ed, he already discussed and talked a lot about this replication crisis problem. So I will just add few more things with his talk. So first one is the studies in empirical research. So when we think about the empirical research, we actually think about the experimental studies. So we have basically two types of studies. We have exploratory studies and confirmatory studies. So as Dr. Ed already said, the exploratory studies bring possible new ideas and innovation in a particular research field. And on the other hand, the confirmatory studies, which confirms a previous finding or result by replicating prior research. So from that confirmatory studies, we are having the word replication. So I will start with the definition of the replication, like what is the replication is. So if in a common understanding, we can think that, okay, replication is repeating a previous studies procedure and observing whether the prior finding occurs or not. So this definition is actually intuitive, easy to apply, and incomplete. So Nosek and Arrington in 2020, very recent paper here, they actually came up with a very formal definition of the replication. So in their paper, they mentioned that replication is a study for which any outcome would be considered diagnostic evidence about a claim from prior research. So what does actually it mean? So it means that any outcome, so that outcome can be successful or that outcome can be unsuccessful. So let's think about the successful outcome, the outcome we celebrate, the successful replication. So in general, like when a replication is successful, it provides evidence of generalizability across the condition that inevitably differ from the original study. So what it increases the confidence on the prior research. It is saying that, okay, the theory, the finding of the prior research is more valid, definitely. And on the other hand, the unsuccessful application, in common sense, like it actually decreases the confidence on the prior research. But the question is, are the unsuccessful publication useless? The answer is no, because the unsuccessful replication actually not saying that this is totally false or something like that. It's giving us more diagnostic evidence from the prior research. It's saying that the reliability of the finding may be more constrained than recognized previously. So basically, the replications that are not successful and suffer from a problem named file drawer problem. So the term actually provided by Rosenthal in 1979, he came up with this term when he described the unsuccessful replication. So basically, the unsuccessful replication of the file drawer problem is a bias toward publishing successful research or significant results. And therefore, that we are just celebrating that something very significant in replication work or something very successful in replication works. And the unsuccessful replication could be stored away in someone's file drawer. And we don't know about that. The people are doing that. We don't have any idea about this. And this is actually the problem with the unsuccessful replication. And they're actually suffering from file drawer problem. So let's think about like what actually the goal of an replication study in empirical research. So it's actually do mainly four things. So trying to prove four things is verify, validate, generalize, and establish the prior theories, hypotheses, model, or findings in a research community. So when someone wants to do the replication study, this is actually the primary goal of doing this. So these are just the introduction. Is there any questions on this part, like successful and unsuccessful replication, the goal of the replication? Is there any questions on that? Okay, cool. So next thing, we will focus on the replication typologies. That means the replication types. So the next few slides is very interesting, and I'm also very surprised seeing this. So basically, when we talk about the replication has different type, and it does not rely only on a particular research discipline. You actually rely on it from which discipline you are coming from. So there is no general replication classification. So in order to explore more, I found actually found a paper, Replication Types in Experimental Disciplines. And from that paper published in 2010, and from that paper, we found that there are they found 18 replication classification, just the classification. And if you consider all of them, and altogether, there are total 79 replication types, which is quite a lot. Yeah, that's actually quite a lot, and that is actually very surprising. And they mentioned that actually all the replication classification is not from a particular field. They mentioned in their paper that 61% coming from the social science, 33% coming from the business, 6% coming from the philosophy. And they also provided a classification chronology. That means like people provided the classification from when and until 2010, because they published the paper in 2010. They found that the social science classification, those are the oldest one, and the business and philosophy, they are the more recent one. So we actually decided that let's see which one actually most often cited classification among all of these different classification, replication classification. We found that the Likings one and the Hendricks one, these two actually most often cited in the different research field. And so the next few slides, will discuss like what actually those classifications telling us about different type of replication. So let's look at the Likings classification, how he actually classified the different replication type. He provided that classification in 1968. And there are basically three types he mentioned. One is literal replication, operational replication, and constructive replication. So let's start with the first one, the literal replication. What actually it means, what actually he means with that. It's mentioned in the paper that the literal replication is doing the exact replication of the original investigators did, like considering the experimental procedure, sample analysis method, experimental condition, everything should be the exact and duplicate. And it's mentioned that it's like something like asking the same author doing the same experiment with more participants or run more subject like this. So he mentioned this type of work as a literal replication. So the next is the operational replication. So the operational replication means the original investigator published the paper, he has published the experimental recipe. Now you have the recipe, and now you will see that can you get the same results or not. So that means that you are using the published or original investigator and experimental recipe, I mean experimental procedure, experimental design, independent, dependent, all the variables, and then you are trying yourself to test whether you are getting that or not. So that is like operational replication. The third one is constructive replication. So the constructive replication is like you are coming with a totally different method. You are not like considering the original investigator's method. You're coming up with your own method, but you are exploring the same research questions. I mean, the same research fact in your field. So that he classified as a constructive replication. So there's a literal replication, there are operational replication, and constructive replication. So let's see about the classification of Hendricks. So what actually he said? This one is more recent compared to the previous one. He also classified replication in three types. One is strict replication, partial replication, and conceptual replication. So the first one is the strict replication. He mentioned that the strict replication aims to replicating the original study as exactly as possible, focusing on the experimental procedure and contextual variables. So therefore, it means that you are considering the everything exactly like the original experiment. So if you as you can see that it actually highly matches the replication classification of the likings, the literal replication. So there's some similarity between these two. The second one is the partial replication. So the partial replication means you have the experimental, you're considering everything the same, experimental variable, experimental procedure, everything, but you are doing some changes. You are adding or you are deleting some of the things from the original experiment. So this is like the partial replication, and which is very similar to the operational replication that we already discussed. The third one is the conceptual replication. It's saying that using the different methods to test the same research question, earlier findings of the prior study. So that means you are coming with your own method, but you are exploring the same research question of the prior study. So this is the conceptual replication. So you can see from these two classifications that whether they're terming differently, but the inner meaning, the inner definition of these two replications are the same. Like they're saying they're doing exactly the same thing. Okay, you can change something. Okay, you're coming up with a new method and do the work and explore the same research question. So though they actually term differently, their inner meaning actually the same. I mean, not the same, very similar. So these are actually the replication types. And any questions on that? Different kind of replication types. Is there any questions? Okay. Yeah. So the next thing is we're planning to talk about the replication studies in human-computer interaction. So why human-computer interaction? Because I believe, and everyone actually agree with me, that this is very much related to our work. So let's see actually what actually is happening in the human-computer interaction research in terms of the replication. So we found a paper, the title like "Is Once Enough on the Extent and Content of Replication in Human-Computer Interaction." This paper published in CHI conference in 2014, and it actually explored the replication studies in human-computer interaction and in very details. So they considered all the papers from 2008 to 2010 from a key conference on human-computer interaction and 3 highly ranked journals. However, they have some certain criteria. So they consider all the papers, but they are mentioning some criteria, like the paper should be the empirical. That means that there's some empirical analysis or empirical experiment will be there. It should include only the quantitative data, not the qualitative data, because they believe that the qualitative data depends on other notations and other stuff. And that paper should report an experiment. And the paper should study human interaction with user interfaces. That means that they are not considering any papers. They are talking about different computational models or comparing algorithms. So they're all about the empirical and empirical human study, user study. All of this will be the part of their certain criteria. So from there, they found total 429 eligible papers from 891 papers. So they found total 891, they found 429 eligible papers. The next question is, then what should be considered as a replication? What counts as a replication? So they mentioned that when a paper attempts to confirm, expand, or generalize an earlier findings, they will consider that as a replication paper. So for considering these, they found basically 3 types. One is replication, one is multiple studies, another is number comparison. So from just you know that what is a replication, that confirm, expand, and generalize. But what is actually the multiple studies type they found? So it actually mentioning that you have a paper, and in the paper you mention multiple studies. For example, experiment 1, experiment 2, so on and so forth. And you're mentioning in your experiment too that, okay, we're having the same experimental setup like the experiment one, and there we are exploring this thing, or sorry, we are adding or deleting this part from experiment one, but we are actually replicating or doing our experiment one. They consider that type of paper as a multiple studies paper, not as a replication paper. Other type of paper is like a number comparison. So the number comparison means that you are doing your you are doing the analysis, you are getting a result, a number, and you are directly comparing that number to the previous work. So that means that you are just comparing the number, but you are not comparing the experimental setup. You're not comparing the experimental variables, anything, just the number. So that type of things they consider as a number comparison paper. So let's focus on just the replication, and you can see from the table that they divided total replication papers in three types: strict replication, partial replication, and conceptual replication. Basically, they consider the Hendrix classification of replication. And from there, they found total 28 replication papers, which is basically the 6.5% of the eligible papers. And if you consider the whole sample size, it is just about 3% of the full sample. So the next question is, are earlier findings confirmed? That means that how many are successful and how many are unsuccessful. So they found that from their replication papers, 50% paper performed successful replication, 3 papers failed to replicate findings, and 4 papers are undefined. So this is really interesting that from their 28 eligible papers, 50% already performed successfully replicated. Why? So maybe the reason is the file drive problem. Maybe they have done successful replication, but then didn't report that, or they didn't publish that, or afraid of publishing, or afraid of accepting that paper. But that means that they're just celebrating the successful replication paper, something like that. So the next question is, whose work is actually replicated? Like, who is actually replicating those work? And they found that 22 studies replicate the work of other researchers, and 2 studies replicate their own work. Therefore, that means that 22 studies, the researchers actually replicating the other people's work, and 2 studies replicate their own work, which is actually pretty impressive. Like, in general, or in other papers, other researcher mentioned that when a non-author's person replicate other papers, that's the better replication, because there is a less biasness can occur when performing the replication. So they prefer that kind of things, and which is quite interesting that in HCI, 22 studies replicate the work of the other researchers. So they actually did a pretty interesting thing. So after having all the data, they contacted the authors of that selected replication papers, and they're asking their review and their thinking of about the replications. And so only 13 the authors reported that their work contained replication. That is good, but the next thing is very surprising. But they mentioned that their main goal was not to replicate the original study. What is their main goal? Their main goal was to research new additional topics and extend the original work, but they are doing some sort of replication. Then their main goal was not the replications, and maybe they're not reporting that in their paper. But this is basically the one sort of replication paper, because in order to extend the original work, you need to do the original work, and then you're doing the extending. So some type of, if you consider different type of replications, it will go within one of the type. So which is quite interesting. Like, do authors doing the replications, their main goal was not actually replications. Their main goal was to explore new research ideas or extend the original work. So this is quite interesting. And not only this paper, like other paper in HCI research, there are other authors, they are talking about the replication crisis and replication important in human-computer interaction. And interestingly, they also arranged a workshop in KAI 2013, and they actually just for the replication papers to discuss, which is quite good and which is very impressive and pretty nice thing that those and that research field researchers are talking about this. So, is there any thought and is there any questions so far, like the replication studies in human-computer interaction? Any questions? Any thought? Nice, great. So let's look at other fields, and one more field, like human factor research field. So why human factor research field, and which is also very highly related to our augmented reality virtual reality research field. So let's see how the replication studies is going on in the human factor research. So in order to explore that, we consider a paper, an investigation of the prevalence of replication research in human factors, which published in the Journal of Human Factors in 2010. And they actually also systematically analyze the replication work, replication research in human factors. And their method of analyzing and replication papers are quite a bit different than the HCI paper I have discussed. So they consider two types of articles. One is the parent article, another type of article is the child article. So what actually the parent article? They considered the 1991 issue of the Journal of Human Factors, and from there they mentioned some certain criteria. They mentioned that this paper have the replication material and other criteria, and from there they selected 8 articles from that particular issue. That's their parent article. So what is their child article? The child articles are the articles that cited that parent articles between 1991 to 2006. So the child articles, the articles that actually cited the original or the parent article. I mean, that 8 articles. And after that, they did a comparison with the child article and the parent article, and they found that which one is replicating the parent article and which one is not replicating the parent article. And when they found any non-empirical papers, they actually totally omit that. So this is their method of analyzing the research, replication research in human factors. So the question is, where human factors studies replicated? So the answer is yes, there is a replication in human factor research. And they found that the total of 30 replications according to their method of analysis. And if you look at the graph, you can see that in the x-axis, the parent articles, A, B, C, D, E, F, G, H, 8 different parent articles, and the y-axis showing how many times that article actually replicated. So here you can see that the article A is replicated 10 times. So they mentioned that the frequency of the replication is 0 to 10 times, and the average is 3.75, which is quite a good. Other thing is very interesting to look. If you look at the circle, that meaning what type of replication they are having. So they've mentioned that they didn't find a single strict replication work. They found only the conceptual and partial replication. Why only conceptual and partial? Why not any exact replications? Well, they actually provided some of their thinking. I just want to share with all of you. They mentioned that one of the reason is like the contribution, degree of contribution to the research, or saying that, okay, we did some good thing. Like, think about the riskiness. So if you do the exact replication, you are using the same thing, exactly the same, no difference. I mean, no basic difference on the experiment. This is their exact replication. So in your partial replication, you are changing something, and conceptual replication, you are coming up with your own method. So there is a thinking among authors that, okay, if I do the conceptual, the higher riskier one or the medium riskier one, maybe my degree of contribution to the research is higher. So that's for that reason there, one of the reason could be that. So that's why they actually focus on the conceptual and the partial replication. And other reason could be that as human factor is a multidisciplinary research field, so someone from the medical domain want to replicate in a theory which actually established in aviation research. So in that case, there are going to be no strict replication, whether the replication could be conceptual or the partial. So this is the reason, like why not having a strict replications, or maybe there are other reasons there. So they actually found the conceptual and the partial replications. So the question next, were the replications successful? And interestingly, they found that 92% were successful replications and 2 unsuccessful replications. What could be the reason for that? So I believe that one of the reason could be the file dryer problem with the unsuccessful replications, like the biasness of publishing only the successful research, celebrating only the successful results. So that could be one of the reasons that when the replication is successful, that moment they are only reporting that the unsuccessful replications is not actually reporting. That could be one of the reasons. So that's why maybe the number of successful replications is very higher compared to the unsuccessful replications. So the next question is quite interesting, like any variation of the word replication, replicate or replicated used in the paper. So they found that only 6 of the 30 replications, like just 20% paper, use the word like the replication, replicated in their papers. And 24 publications or 24 didn't mention any language like this. So isn't it very surprising? Like, okay, there's a replication papers that, but they are not using the word or anything like replicated, replication in their work. So what could be the reason? So the reason could be that authors may not have known that their research was a replication, or may not have considered their research to be a replication. So like the HCI research field, they also want to explore new research ideas, want to extend the previous work, and they're doing their work, but they actually didn't know that their research was one of the replication type research. So that could be one of the explanation behind this. So the next question, who conducted the replications? And from here you can see that 11 of the 30 replications was done by the original authors, and 19 of 30 replications, which is 62%, done by the other authors. So other interesting things is to look here. If you look at the particular partial replication or conceptual replication types, so just considering the partial replication, you can see that replication of the same author is higher than the replication with the different authors. And also, if you look at the conceptual replications, here's the opposite things. The same author number is lower, but the other author number is higher. Why? The reason is that when you have seen that a paper is published, they have finding exploring this research method. But when you think that, okay, I don't need to come up with a new idea, I need to do a different method. Can I get the same results? I don't know. So from that tendency could be the reason of having more conceptual publications by the different authors rather than the same authors. And in the partial replication, you can see that you can just doing slight modification of your experiment. So that actually mostly done by the original authors rather than the different authors. So what are the key points here? The first key point, obviously, that replication exists within human factor research. The second key point is exact replications are rare, whereas conceptual and partial replications are more prevalent or relevant, I mean, more frequent. And the third point is very interesting. Replications are not always labeled as replication, so it is very difficult to identify them. So if I compare the replication studies with the HCI and replication studies in human factors, I found 2 common things between these 2 research fields. The 2 common thing is exact replications are rare. I mean, rare means a few, very few compared to the partial replications and conceptual replications, which are very common. And authors of replication papers rarely identified their research as replication, which is really quite interesting because when they're writing their review papers, they're comparing the experiment. But the original authors, actually, they didn't focus on the replication. They only focus on extending the work or bringing new ideas or new research in the field. So I think this is a two interesting fact about these two research fields. So is there any other thought on this or any other questions on regarding this?
Do you think that these interesting facts are uh, because the field of research does not support this type of works so well yet?
So if you look at Dr. Ed talk, he actually in the final part of his talk, he mentioned that the review process, how we should consider that. He provided some recommendation. Maybe the same recommendation can be applicable to that HCI research or human factor research to value more replication work. Because if you always celebrate with the successful replications, and then you can see that uh, there's a few unsuccessful replications. And when you see that number of successful and unsuccessful replications increased, then you can use those word or keywords in your paper. So as Dr. Aid showed one of his slide that, okay, this is not surprising. This is as usual. There's nothing novelty there. Maybe that could be the reason in this research field. It could be one of the reasons for this. Well, thanks for asking the questions.
Okay, thank you. Thank you.
Yeah. Is there any other questions? Okay, cool. So let's move to this final topic, the replication studies in augmented and virtual reality. So based on our knowledge and our exploration, we didn't find no research paper has systematically investigated replications in augmented reality and virtual reality. So therefore, we do not know the extent of replication in augmented reality and virtual reality and the content of those replications. But if one want to explore that, I think the most challenging will be to identify the replication works, because replications are not always labeled as a replication. So it could be one of the challenging things if you want to explore or investigate the replications in AR and VR. So the last topic, like contribution from our current research, in very specifically from our lab, the Spatial Perception and Augmented Reality Lab, run by Dr. Ed. So what actually we contribute in this replication crisis, what type of studies we did. So I will discuss a very recent work. So we actually considered this paper, the effects of AR display context switching, focal distance switching on human performance by Gavert, Mehra, and Swan in 2018. Thus, this paper published in IEEE TVCG. And they're exploring the AR display context switching and focal distance switching effect using a very unique and very old display, Nomad AR display. So we're thinking that their results could only be related to that particular display. What about if we use other display and if we replicate their work? So what we did a partial replication. We actually adapted their same experimental task, same procedure, same experimental variables, independent and dependent variables, but we actually did some modification. We used a different AR display and more complete experimental design. What does it mean? So if you look at this paper, you can see that in the experimental design, there are some cells, a cell that doesn't have any value. So we actually collected more data to have more complete experimental design and also consider a different AR display, more powerful AR display, the AR hyperoscope. So both display has the ability to put virtual objects at different focal distances. And we did the partial replication, and the abstract of this work is all accepted in IEEE VR 2020. And so let's see the graphical comparison of two experiments. So I'm not discussing the statistical and the other stuff. I'm just focusing on the graph. So if you look at these two graphs side by side, these two graphs are from the two different experiments, two different work, and two different air display. But if you compare these two graphs, you can see that you cannot, you can hardly differ these two. And therefore, that means that we actually successfully replicate the experiment of Gavard, Mehra, and Swan of 2018. And we found that focal distance and context switching have significant impact on user performance and eye fatigue. So what is the benefit of doing that replication? What actually get? So we actually get that we found that this context switching and focal distance switching are general optical see-through AR interface design issues. And this finding, the hypothesis of the previous work and hypothesis of our work are consistent. We can say that this broadly generalized to optical see-through AR user interfaces. So that's actually the beauty of doing a replication work. And we also mentioned clearly that in the title of the work, this is actually a replication works. So that's basically from all my side, from my part. And here are the references I used in this talk. So if you have any questions, anything, any thoughts, you can ask me.
And I'll mention that I'm also here.
Yeah.
At Swan. So the two of us are sitting side by side, but it's,
okay.
It's the speakers right here kind of between us. Let me mention one more thing. So I'm going to end the second talk and put the first one back again for a moment. So these are the references from the first talk and some contact information. And in particular, I will point out the slide location. As soon as we're done, basically, I'm going to create a PDF version of both presentations and put it on this website in this location. So are there any final questions? And I'll ask Arfan to look at the Wahova app or whatever to see if anything has come through there. Is this happening? Well, that was kind of a philosophical question.
Yes, I was actually asked it in the beginning.
Okay.
So let's check.
And then there's also a YouTube, I guess, of this talk. And then there's also a YouTube, I guess. And there's my voice again. Yeah.
So the question from that slide.
Okay. All right. So I think Arfan and I will sit here for a minute while I create this PDF, and anyone who wishes can ask a question or talk to us. This is like the point when the tutorial is over, when you can just walk up and talk to the people who are there. And I'll also take a look at the virtual environment here. And I'll take a step into the middle of the room.
Hello. So maybe I have a question, but I feel a bit bad because I was basically just joining very late because we had another tutorial running in the in a red room. So maybe now my question is just very stupid.
Hello,
but
Stephanie. No stupid question. No stupid question.
yeah, so sorry if you answered this already. So, but I thought, since nobody else was asking something, I can maybe just jump in and just ask something. Do you think that the crisis is basically related, that it's often not quite clear? And I think this was maybe something that I just saw from the last presentation, that it's often not quite clear if it's a replication study. So because I can't really remember to read like a paper where it was explicitly saying, okay, we now come and completely replicate this in this experiment. So the most stuff that I usually read is that you have the feeling that there are some parts which are basically replicated, but not so much that you think, okay, somebody really took now an effort and wants to replicate the whole thing.
So the word crisis, that's kind of alarming, but so the crisis was adopted by, in part, the popular press within the past 10 years. And the crisis came from some really shocking inability to replicate treatments in medicine. So here are some of the articles, again, in the popular press that were published. Here's one that was published in a medical journal. Why most published research findings are false. How much can we rely on published data on drug targets? Cancer research in crisis, are the drugs we count on based on bad science? And the most pessimistic of all, from 2016, 4 years ago, 4.5 years ago, big science is broken. So the problem was, Here was the problem. So this is what led to the word crisis. So in 2011, 95% of cancer drugs failed in clinical trials. So clinical trials are very expensive, involve hundreds, thousands of people. 95% of these cancer treatment drugs were failing. And that led to some replication studies on drug effectiveness. And here, all in medicine, these top 4 ones, black, the number that were replicated. Look at this last one, the ALS Therapy Development Institute. That's Lou Gehrig's disease, a terrible disease. 0 out of 47 studies were replicated. So that's where the word crisis came from.
Yeah.
Arifin found is in the field of human factors that, we couldn't really call it a crisis. What he found, some scholarship that I've never seen before, but it's very interesting. And he's right here as well. He found that one issue is that replication is often not used in the paper. So this was
one of the things I found very interesting is like when they're in human factor in HCI, the review papers, they're comparing the replication papers with the original papers, but the replication papers, they're doing the replication, but their main goal was not to do the replication. Their main goal was to do the extension of the work or finding new research. And also, they actually didn't mention the word like replication, replicated in the paper. So, but when they're doing the analysis and investigate those papers, they compare the method and everything, they found that this paper actually replicating either on one of the type of the replications, and then they further working more. But the part they're doing as a replication, they're not occasionally mention that, like 6 out of 30 papers mention that they're doing the replication. And this is quite a small, like those are all of them are replication papers, and 6 mention the replication, replicated, those keyword or key term in the replication in the papers, which is quite interesting.
So in this finding here from the replication of psychology papers, they found 36% were reproduced. That seems too small. But as Arifin pointed out, we don't know what this number is in our own field.
Oh, we don't know.
Nobody's,
we don't know.
Nobody
I actually
has,
explored. I mean,
nobody has systematically done it, but the paper is essentially waiting to be written. And Arifin has uncovered example papers from even more related fields of chi and human factors.
So in chi,
showing showing ways to do it.
Yeah, they actually showed like how to explore. I actually showed that in my slide. Like in the paper, they mentioned that how they extend and explore the replications in HCI. Also, other paper like in human factor, they mentioned that if you want to do what is the procedure? They also, I mean, they mention in HCI field, and that's cool. That's a very cool thing, like in HCI, which is very quite related to our field.
Yeah.
Yeah. But I didn't find, based on my knowledge and our knowledge, I didn't find any paper that systematically actually investigate the replication studies in augmented reality and virtual reality. I believe there should be some, but it needs to explore.
Yeah.
So do you think this would get a bit better with for AR, for instance, now that it's a bit easier to basically, distribute, for instance, apps, and usually like a lot of people are using similar frameworks to implement their AR solutions? Because I think in the past it was often a problem that it's quite hard to share your code because most of us, they were basically using very complex systems, and it was basically only one person could actually operate the system sometimes. So so maybe this is now getting better since it's just very more accessible.
Yeah, definitely the new generation of AR displays, HoloLens, Magic Leap, that should definitely help a lot. And the cost of one of those displays compared to the cost and equipment and time just 5-6 years ago is, at least an order of magnitude cheaper. So I think this will change. It's possible also that, using these devices is now part of chi. So, the research is spreading beyond just
yes, that's true.
Just our community.
Yep, that's true.
I mean, many people who attend ISMAR and VR also attend chi, so there is overlap in the communities as well.
That's true.
And I mean, there are also these kind of nice initiatives now with the, these kind of code replication stems that you can get if you submit your papers to some journals, which are maybe also like an incentive for some authors to basically share their code, which is, I think, still not too often happening within our field.
Not too often, but I've seen a lot of that starting just in the last year, the last 2 years. So maybe there will soon be more of
it. Do you mind if I ask a question, Stephanie?
Yeah, please.
Sorry, Francisco here.
Yeah.
So, okay. So what do you think about these papers that discuss failure? So maybe this can also help because we discuss problems that we face. So maybe it can be interesting to have this type of studies and processes being put in, I don't know, in challenge for more times. And I don't know.
It would be pretty hard to get a paper published, or at least I would think it would be hard to get a paper published that was only talking about failure.
Oh, yes.
So one idea there is the pre-registration of research plans. So here it's, before you run the study, you've registered that you plan to run the study. And this also creates a place for putting the results of the unsuccessful study. So the results can be put in the same place. And then even if the results are not accepted by a journal, they are at least out there. Oops, I accidentally went forward.
Yeah, so That's true. I mean, if you look at human factors and HCI, so the review paper I found and discussed, like if there's 30 replications in human factors, like 28 is successful replications and just 2 mention the unsuccessful replication. So if you compare that to and with the 28, so you can see that the people are actually focusing on the successful replications and they're actually not focusing on the unsuccessful replications. Also in HCI, the same thing, like they considered 28 papers and I mean, they figure out 28 replication papers and 50% of them is actually the successful replications. So most of the paper in HCI and human factors, most of them are successful replications. So the unsuccessful replications is actually very few.
Thanks.
So around here, it's like dinner time. So I wish we could all go out to have a dinner. That would be the nice
Yeah, for
next
us it's lunch.
lunchtime there.
Yeah.
Yeah, actually, for you, it's lunchtime tomorrow for us. So lunchtime.
That's right. Yeah, I say hello from the future.
We haven't eaten dinner Monday night yet. Isn't that great?
Here in Brazil, almost dinner, but after organizing the first day of ISMAR, everyone is just talking a lot here in the lab. Lots of people.
Just afternoon for me, but I've been up since 2 a.m.
2 a.m. Good Lord.
Yeah, it's a little awkward for the West Coast.
Yeah. So that's Kai. Hey, Kai. Wish we were jamming this year.
Yeah, maybe next time.
I sure hope so. That would be fun. Fun. I look forward to meeting in person again very soon. It's a crime that we're not all in Brazil. What a cool place. Beautiful place.
Yeah, we really wanted to have you all here.
I know, I wanted to go.
Amazing.
And then VR this year in Portugal. Don't look like we'll get to go. Oh, what a crime. Portugal. Beautiful place.
Yeah, definitely.
Fantastic food.
Exactly.
Yeah.
Yeah, it's a pity. Yeah, I was also looking forward to Lisbon.
Yeah. I was in Spain previously, in the before times. And only a little bit farther to get to Portugal. So would like to go. So I'm gonna continue to make the slides into the PDF form. Let's see.
Yeah, I will maybe say
Interestingly-
goodbye. Thanks a lot for the interesting discussion, and sorry if I was asking any questions that you just answered before.
Oh, no.
So,
It's very, teaching, it's supposed to be a conversation. It feels weird just to talk in my regular office to my regular stuff all around me, So it's very nice to have some conversation. I only wish it could continue. That's what I
that's
wish.
right.
Well, I think it's getting late enough and I'm getting tired enough that I might need to continue the conversation tomorrow morning.
That would be very nice. Yes.
Okay, well, I will see you later.
I hope I encounter your avatars somewhere.
I've been walking around. It's a nice little island.
Yeah, it is. Yeah, I was walking around trying to figure out how to navigate and so forth.
I gave some suggestions to the infrastructure company about more consistent controls. We'll see if that gets anywhere.
So Kai, I'm part of another project that purchased some Matterport cameras. So it's interesting to see that.
I'll
Think about you.
I'll be curious if you do anything interesting with them.
Well, we're building models of buildings. So I think that's what they're made for.
Well, if you ever need help with something, just feel free to reach out. I can probably get high-res meshes if you need them.
Oh, okay. So let's see. We're talking through Zoom, but here is your avatar. So
You can see your own avatar here.
Oh yeah. I walked into the room and then realized you guys were all on Zoom, so jumped over. I did notice that the audio quality through Zoom is much better than the YouTube live stream.
Yeah, I think the Zoom people, that's their core business, is making that sort of thing work.
Yeah, it was odd. The YouTube had I think the audio is echoing and you can barely understand it.
Let's see, I gotta.
You can dance, you can have samba.
Yeah. For that, Kai, I must say sorry, because I was running through the campus solving other issues. I need to say the same sorry for Professor Ed, because I just came in the end, but the part I saw was really nice. But that noise problem, that echo, it's because they were taken with 2 microphones. So then we solved that. So in the end, it was far better in the YouTube. So sorry about that. Yeah.
I mean,
because it changed it so fast to Zoom. So that was just something that was there.
Half the time these the workshop days are used as a technology shakedown session anyway, make sure everything works.
Apparently the first part of the talk was rough, but because of the audio quality.
Yeah, but it was possible to hear you. I was there most of the time. It was okay.
Okay.
But
well,
it's possible to understand. It was a little bit annoying because of the cuts on the voice, but it was possible to understand.
Okay.
It's okay.
There's Arifin. You can see. Oh yeah. Let's see how I shake hands. So I think I have to face you. Arifin, of course, is physically like right here. Boy, this would be so quick if we were all together. Ah, there you go. That worked. That worked. Let's see. How do I shake hands? Here we go. F3. So I'm ready to shake hands with someone. There we go. All right.
You can also type /shake in the chat menu, and I think they also have some undocumented commands too.
There we go. All right. Wow. That was
nice.
I look forward to shaking hands in person again and not having to wear masks in person and all that. That'll be very nice.
Well, I have hopes for next ISMAR next fall.
Yeah, I do too. Yeah. I definitely have hopes for that.
Ooh, well, I think I really do need to head off now so I can.
Me too. I'm hungry and we're fatigued.
I will see you tomorrow.
All right. So very good to see everyone. I guess I will leave the Zoom meeting and hope to see you all soon.
Thank you.
Yeah.
Thank you. Bye-bye.